Hello folks, today we're going to be talking about intermolecular forces and the idea of polarity and what this all means. So if we just break down the word intermolecular, inter means between, so we're talking about forces between molecules. And when we talk about the idea of polarity, we're talking about the idea of like poles in a magnet, the idea of one end is slightly positive and the other end is slightly negative. So we first have to refresh our memories on electronegativity and what it is. Electronegativity is the ability, or it measures the tendency of a bonded atom to attract electrons. Basically, it measures the attractive force by an atom to electrons from another atom that is bonded. Okay? The most electronegative element is fluorine, and it's all related to the size. Fluorine is one of the smallest elements on the periodic table, next to like helium and neon. And however, it is trying to achieve that octet so it can reduce its potential energy. Okay? So the questions today are, what would happen when an atom with a slightly higher electronegativity is attracted to an atom with a lower electronegativity, and they're bonded covalently? Will the electrons actually be shared equally? And how will this affect the way it interacts with other similar molecules? Okay, because remember, molecules are not going to be found as a single entity. There's going to be hundreds upon billions upon trillions upon quadrillions of all of them. Okay, so the first thing we're going to be looking at is the idea of fluorine. If fluorine is bonded to another fluorine, okay, so a couple things I'm expecting you to be able to do is, number one, being able to use a periodic table, and from that periodic table you can determine the number of valence electrons, and that you can also draw, for example, a Lewis dot structure, okay, a Lewis structure of fluorine. All right, so the first thing I want to ask you is, what type of bonding would be forming here? Would this be ionic or covalent? And I'm hoping that all of you are answering the idea of covalent, because they are two nonmetals with very high electronegativities. And because they have very high electronegativities, what ends up happening, all right, is that when we have our fluorine, which has a total of 7 valence electrons, comes into contact with another fluorine, again, that has 7 valence electrons, what will end up happening is that it will share a pair of electrons. And we can draw this in a different way so that we show a line that represents the 2 electrons that are being shared. And we will notice that we still have our lone pairs of electrons that are not being shared. Now here's the thing. This fluorine has an electronegativity of about 4.0 on the Pauling scale. And this fluorine, because they're identical, has a Pauling scale on the electronegativity scale of 4.0. So literally they are pulling the electrons with the same force in either direction. They are literally having a tug-of-war battle, and no one is winning. Okay, everyone got that? No one is winning. All right. So what does this mean? Well, the question is, are they sharing their electrons equally? And the answer would be yes, they are sharing their electrons equally, because of the fact that their electronegativities are identical. Now, what happens if we change the scenario? What happens if we have fluorine, ladies and gentlemen, all right, that is now bonded with, instead of another fluorine, it's bonded with hydrogen. Now, if we look at this and we're examining, first off, hydrogen is a nonmetal, fluorine is a nonmetal. So my question is to you, what type of bonding is going to take place? And I'm hoping that all of you are saying, covalent. And the reason it's covalent is because of the fact that we have two nonmetals. Their electronegativities are relatively close to each other, but here's the key, not exactly the same. So what will end up happening is, again, we will share electrons, and we will have fluorine that will have a total of, now, the total pairs of electrons there, and a bond to the hydrogen. Okay? Now, the question is, based upon their electronegativity. So fluorine has an electronegativity still of 4.0 on the Pauling scale. Hydrogen, on the other hand, has an electronegativity of about 2.1. So remember, it has to do with the electronegativity determines how much pull it's giving. So fluorine is the biggest. So this would be like, let's just say fluorine is like John Cena, and hydrogen would be, me. And so the idea is that, ladies and gentlemen, this would not be an even tug-of-war battle. There would be a lot more force pulling the electrons towards fluorine and a lot less pulling to the hydrogen. So therefore, the question is, would the fluorine and the hydrogen share the electrons equally? And the answer would be, no. The answer would be no, ladies and gentlemen. They would not be sharing their electrons equally. Well, what does that mean if they're not sharing them equally? What that means, ladies and gentlemen, is that the fluorine is actually pulling the electrons closer toward it. And because it's pulling the electrons closer toward it, the fluorine actually starts to get a slight negative charge. Okay, this little symbol is a delta symbol to represent a slight charge. Everyone got that? A slight charge. So this becomes slightly negative. Well, if one end becomes slightly negative, the other end has to become slightly positive. So literally what we've made is what we refer to as just basically a mini magnet. Okay, a mini magnet, ladies and gentlemen. All right. So imagine if we had a bunch of these together. What's going to end up happening if we have a bunch of fluorines and hydrogens that are bound together? Are they going to start to align themselves up? Okay, and that's what we're going to be examining over the couple slides here. Okay, so that leads us into this thing called intermolecular forces, forces of attraction between molecules. And so what I want you to do is to examine, locating over here on the right-hand side, the boiling points. And what I want you to notice with the boiling points, look at what we have here. We have a nonpolar covalent, meaning, look at that. That is two hydrogens, ladies and gentlemen. A hydrogen bound to another hydrogen. Their electronegativities are exactly the same, which means that they are sharing their electrons equally. And if you look at their boiling point is very, very, very low. That's a negative 253 degrees Celsius, ladies and gentlemen. On the other hand, water, we have oxygen and we have hydrogens bound to the oxygen. Again, the hydrogens still have an electronegativity of 2.1, but the oxygen here has an electronegativity of about 3.5. Okay? What that means, ladies and gentlemen, is that the oxygen is not sharing the electrons equally with the hydrogen. And notice the boiling point goes to 100 degrees Celsius. Then we look at sodium chloride. Sodium chloride, ladies and gentlemen, has a boiling point of 1,415 degrees Celsius. And how is it bonded? As an ionic compound, meaning a transfer of electrons. That means those bonds are ridiculously strong to be able to pull it together or pull it away. And for copper, which is a metallic bond, which we'll talk about further on down the road, but look at the temperature at which it boils. 2,567 degrees Celsius, ladies and gentlemen. That's ridiculously high. Even stronger forces holding it together. So here's the thing. Boiling point gives us an idea of how strong the forces are between the molecules. How strong it is, right? And yes, we can make some predictions if we look at their structures. Okay, we examined water already. We examined hydrogen already. But look at copper and look at sodium chloride. They actually make these unique structures in which they actually form what are called lattice structures. There's literally a repeating pattern of sodium ion and chloride ion attracting each other, making it so that they are extremely hard to pull apart. Okay? The same with copper. The idea, folks, is that the electrons can actually just flow through the substance very easily. That's why we use it in wiring. Okay? So there are two main types of intermolecular forces that we need to talk about. And the two main types are dipole and London dispersion. Okay? Now, a dipole, just think about the name, di. Di, I hope you remember from way back when, means two. All right, so what we're talking about is two poles, meaning one end that is slightly negative and one end that is slightly positive. And then we'll also talk about another force called London dispersion. So the first one we're going to be taking a look at is dipole. Okay, so a dipole, by definition, is equal but opposite charges that are separated by a short distance. Okay, dipole depends upon two things. When atoms of differing electronegativity are bonded to each other, and the shape of the molecule. That is the key. The shape of the molecule, all right, as well as the differing in the electronegativities. So I have a couple examples that I want to run through, all right? I've got oxygen, O2. I've got water. I've got ammonia. I have a substance you've probably never heard of, which is carbon tetrachloride. And then also we have carbon dioxide. So I'd like to look at these structures, and let's take a look and see if we can determine whether they will have a dipole or not, meaning one end that's slightly negative and the other end that is going to be slightly positive. Okay, so the first one, let's take a look at oxygen. So oxygen, all right, we have our 6 valence electrons. They will form a bond here and a bond here. So if we clean this up and draw it neatly, we end up with oxygens bound by a double bond. Now, are their electronegativities going to be the same? Yes. So that means they are pulling in equal and opposite force, which means, ladies and gentlemen, there is no dipole. No positive or negative side to either one of those oxygens. Okay? Now, let's take another look. Let's take a look at water. Water, okay? We've got oxygen, which still has its 6 valence electrons. Each hydrogen has 1 valence electron. So they're going to form a bond. And we're going to end up cleaning this up, and this is going to look like this. Now, oxygen has a much greater electronegativity than hydrogen. And because of this, there's an unequal sharing of the electrons. Right away, you should be able to tell that there's an unequal sharing of the electrons because look at this oxygen. What does it have? Lone pairs of electrons that it isn't even sharing. So that means, folks, that this will have a dipole. Now, if we want to label the dipole, the oxygen is going to be slightly negative and the hydrogens are going to be slightly positive. Okay, slightly positive. Let's take a look at another one. I've forgotten what the other ones are. Ammonia. Ammonia, NH3. Let's take a look. Nitrogen has 5 valence electrons. Each hydrogen has 1 valence electron. We're going to form bond, a bond, and a bond. We're going to clean this up, and this ends up looking like this. Now, if you examine a periodic table, you will recognize that nitrogen is far over to the right in the nonmetal region, and it does have a greater electronegativity than hydrogen. And if you notice, look right here, look, lone pairs of electrons, folks. That means it's not sharing its electrons equally with hydrogen, so therefore this has a dipole. And because it has a dipole, that means that the nitrogen is slightly negative and the hydrogens are all going to become slightly positive. Okay? Now, one of the other ones that we're going to go look at, okay, I'm going to clear the screen here so we can get rid of this and have a little more space. I'm going to look at, ladies and gentlemen, we're going to take a gander at carbon tetrachloride, CCl4. Now, carbon, 4 valence electrons. Each chlorine has 7 valence electrons. Okay? Yes, lots of dots to draw here. Patience. So, we'll form a bond, bond, and bond. We've got 4 bonds. Let's clean it up. Carbon's in the center, 4 bonds, chlorine here, chlorine here, chlorine here, and a chlorine here. Okay, now let's take a look here. Carbon in comparison to chlorine. Chlorine is way far over. It's literally right next to the noble gases. Carbon is not, okay? So chlorine is going to have a much greater electronegativity than carbon, much greater. But here's the key. Is there an equal distribution of chlorines around here? So my question is to you, do you think that this has a dipole or no a dipole? If you chose no dipole, you are correct. And you're going, yes, 50-50, I got it right, but I don't know why. Well, folks, if there's an equal poling in all directions, what we end up with, ladies and gentlemen, is a substance that has no dipole, meaning it's being pulled in equal and opposite directions. Okay, so this is where shape plays a role here. Yes, the carbon and chlorine absolutely have totally different electronegativities, but all of these elements over here on the outside of the carbon are all the same. They're all the same. Okay, that leads me to the next one. Let's take a look, folks. Let's take a look at, and I'm going to erase this. I want to take a look at carbon dioxide, CO2. So let's take a look at carbon dioxide. Carbon, again, 4 valence electrons. Oxygen has a total of 6 valence electrons. What you will notice is we can form a bond here, we can form a bond here, we can form a bond here, and we can form a bond here. So if we clean this up, we've got carbon here, we've got now our oxygen with a double bond, our oxygen with a double bond, and take a look. Look at the shape of this. This shape of this is linear. It's straight. It's in a line. So my question is, do you think there is a dipole or no dipole? If you chose no dipole, you are correct because, again, equal pulling in opposite directions. Equal pulling in opposite directions. Yes, oxygen has a much greater electronegativity than carbon, but that doesn't make a difference because they're both pulling. Carbon just happens to be stuck in the middle of this whole thing. All right? So, when a molecule has a dipole and interacts with another molecule, we call it a dipole-dipole interaction. Okay? Where literally these things act as tiny little magnets to each other. Okay? So, of course, there are exceptions. There are some substances that are polar that can make it so that when they interact with other nonpolar molecules, they can become basically small intermolecular forces that occur. We'll go into more about that later on, okay? But let's take a look real fast at hydrogen bonding is a particular type of intermolecular force, okay? Basically what it is a souped up version of a dipole, okay? But the key thing is it must have hydrogen present, all right? The great example of this would be water. How many of you have ever jumped into a pool in a most unfortunate way, meaning that you've done a belly flop? And it feels like when you hit the water that it's almost as if someone slapped you on the back, or maybe it felt like you hit a piece of concrete, okay? And that is because water has the ability to attract itself, okay? It's tiny little magnets that literally form a network, as shown in the diagram there, where they literally form a network that hold them together. Now, here's the thing I need you to understand. Hydrogen bonding is not a real bond. It's just a very strong level of attraction of intermolecular forces, all right? And so if we look at it, again, that is because we have oxygen that is not sharing its electrons equally with the hydrogen. So if we have another water molecule over here, what we will notice is that these water molecules will become attracted to each other and form a network, okay? Now, the one last intermolecular force we're going to talk about is London dispersion. And this is literally caused by the motion of the electrons. The electrons are constantly moving. But here's the thing, they don't move in a perfect circular orbit, and they also don't all move at the same speed. So what can actually happen is we can create what are called instantaneous dipoles, where literally the electrons here can move and align themselves so that there's more electrons over here than over here. And what we end up with is an area that is slightly negative over here and slightly positive. But because they're moving, what will end up happening is that dipole will just completely disappear. So it's called an instantaneous. It instantaneously occurs. Okay? Now, how can we know when this happens? What does it show us? What does it mean? Well, it means, folks, that if we have something like fluorine. Fluorine, by the way, ladies and gentlemen, in its natural state as F2 is a gas. Chlorine, in its natural state, is a gas. However, bromine, on the other hand, is a liquid. And then iodine is found as a solid. And because of this, this is all because of the electrons. These substances have no dipole. They lack a dipole. Because of their number of electrons, that's what determines whether they're gases, liquids, or solids. So each fluorine has 9 electrons. 9 plus 9 is 18 electrons, okay? Chlorine, on the other hand, has 17 and 17. That makes 34 electrons. And then it continuously gets larger and larger for bromine and iodine. And because we have more and more electrons, we can create more of these instantaneous dipoles. And by the way, every single compound has London dispersion. Every single compound has London dispersion because every single compound has electrons that are in constant motion. I want you to remember this, okay, and associate this. Polar means dipole. Nonpolar means no dipole. So let's take a look. I want you to help me. Again, polar means that it has a dipole, an unequal sharing of the electrons. One end is slightly negative, the other end is slightly positive. Nonpolar means that there is no dipole. So let's take a look at our first structure. What do you think? We got carbon in the center, each hydrogen there. Do we have a dipole or no dipole? If you said that we have no dipole, you are correct, okay? Because of the equal poling in equal and opposite directions. What about now? If you are saying dipole, you are correct because, ladies and gentlemen, This chlorine is pulling the electrons way harder than these hydrogens are. There's a lot less pull. And because there's a lot less pull, okay, we end up with a dipole. What about now? We still have an unequal pulling, a major pull here, a major pull here, tiny pull, and a tiny pull. This again is a dipole. Here, if you said dipole, you are correct. Big pull here, big pull here, big pull here, tiny pull here. What about this? Now we have an equal pulling in all directions. Big pull, big pull, big pull, big pull. This, ladies and gentlemen, would be nonpolar. There would be no dipole associated with it. So here's what I want you to do, ladies and gentlemen. I want you to go back to your activity, and I want you to fill in the polar or nonpolar section on the right-hand side of the column, finishing the activity that you had started previously from the week. There will be a place for you to submit this in Google Classroom.